Imagine a world where gravity is merely a suggestion. A world where liquids dance in midair, forming perfect, shimmering spheres that never touch a surface. A world where surgical tools are replaced by invisible beams of energy, and where you can reach out and touch a hologram, feeling the texture of a digital object against your skin. This is not the opening scene of a science fiction novel set in the 25th century. It is the reality of a rapidly evolving field of physics known as acoustic levitation. For most of human history, sound has been an ephemeral experience, a sensory phenomenon we hear, enjoy, or endure. It is a wave of pressure that travels through the air to vibrate our eardrums. But in laboratories around the world, from high-tech facilities at NASA to university basements in Bristol and Tokyo, scientists are proving that sound is much more than just noise. It is a physical force. It carries momentum. And if you harness it correctly, you can use it to grab, hold, move, and manipulate the very fabric of the material world. Today we are taking a deep dive into the science of acoustic levitation. We will explore the mind-bending physics that allows sound to defy gravity, trace the history from 19th century dust experiments to modern tractor beams, and uncover the revolutionary applications that are changing medicine, manufacturing, and even our understanding of the ancient past. To understand how we can levitate an object with sound, we first need to recalibrate our understanding of what sound actually is. When you speak, you are not shooting a projectile at a listener. You are compressing the air molecules in your throat and pushing them outward. These molecules bump into their neighbors, who bump into their neighbors, creating a chain reaction of pressure waves. These are longitudinal waves, consisting of compressions, which are areas of high pressure, and rarefactions, which are areas of low pressure. Usually, this force is incredibly weak. The amount of pressure exerted by a conversation on your skin is negligible. However, if you crank up the intensity, specifically the amplitude of the wave, and focus it correctly, that pressure becomes significant. You cannot simply blast a speaker at a rock and expect it to float. If you did that, the sound waves would simply travel past the object, perhaps nudging it slightly, but mostly just scattering. The key to levitation is a phenomenon called the standing wave. Imagine you are holding one end of a jump rope, and a friend is holding the other. If you shake your end up and down, a wave travels to your friend. If they shake it back at the exact same rhythm, the waves traveling forward and the waves traveling backward will interfere with each other. At certain frequencies, the rope will appear to stop moving forward and instead just oscillate up and down in fixed segments. This is a standing wave. In acoustic levitation, scientists use an ultrasonic transducer, essentially a speaker, and a reflector, which is a solid surface. The speaker emits a sound wave that travels up, hits the reflector, and bounces back down. If the distance between the speaker and the reflector is perfectly calibrated to the wavelength of the sound, the upward moving wave and the downward moving wave combine. This interference creates two distinct areas. First, we have antinodes. These are areas where the waves add up, creating massive fluctuations in pressure. This is where the air is moving violently back and forth. Second, we have nodes. These are areas where the waves cancel each other out. In a perfect node, there is theoretically zero net movement of air pressure. It is a quiet, still pocket in the middle of a storm. Here is where the magic happens. Gravity is pulling an object down. But the sound field creates a pressure gradient. The air pressure at the antinodes, the loud parts, is intense. The air pressure at the nodes, the quiet parts, is low. Nature hates high pressure. It always wants to move toward equilibrium. Consequently, any object placed in this sound field will be pushed away from the frantic high-pressure antinodes and nudged toward the calm, low-pressure nodes. If you orient this system vertically, you create a series of invisible shelves. As gravity pulls the object down, the acoustic radiation pressure from the antinode below pushes it back up. The object settles into the node, trapped in a pocket of air. To the naked eye, it looks like magic. A water droplet, a styrofoam ball, or even a small insect, floating effortlessly in midair. For the physics enthusiasts, the mathematical description of this trapping force is defined by the Gorkov potential. It calculates the force on a small particle in an acoustic field. The formula reveals a critical limitation, which is the size of the object. For a standing wave to trap an object, the object must be smaller than the wavelength of the sound. If the object is too big, it disrupts the standing wave entirely, destroying the delicate interference pattern that creates the trap. Most acoustic levitators use ultrasonic frequencies around 40 kHz. These frequencies are too high for humans to hear, as we max out at 20 kHz, which is fortunate, because the volume required to levitate objects is around 150 decibels. That is roughly equivalent to standing next to a jet engine at takeoff. If we used audible sound, the levitation would be deafening. At 40 kHz, the wavelength of sound in air is about 8.5 millimeters. This means the sweet spot for levitated objects is roughly half that size or smaller, about 4 millimeters. This is why you typically see experiments levitating small beads, ants, or droplets, rather than bowling balls or cars. The story of acoustic levitation begins long before modern electronics. In 1866, German physicist August Kundt invented a device to measure the speed of sound. He placed a fine powder, usually lycopodium seeds or cork dust, inside a glass tube. When he rubbed the tube to create a sound vibration, the dust didn't just sit there, it arranged itself into distinct piles at regular intervals. Kundt had inadvertently visualized standing waves. The dust was gathering at the nodes, pushed there by acoustic radiation pressure. While he wasn't levitating objects in the sci-fi sense, he had demonstrated the fundamental principle that sound can organize matter. It wasn't until 1933 that Carl Buchs and Hans Müller achieved true levitation. Using quartz crystals driven by primitive electronic oscillators, they managed to suspend droplets of alcohol in the air. This was a monumental breakthrough, proving that the acoustic force could counteract Earth's gravity purely through the medium of air. In the late 20th century, NASA became interested. In space, manipulating fluids is a nightmare. They float away, coat surfaces, and are hard to contain. Acoustic levitation offered a solution called containerless processing. NASA developed sophisticated acoustic levitators to hold hot blobs of glass or molten metal in place without them touching a crucible. This was vital because when a material melts in a container, it can react with the container's walls, introducing impurities. By melting a material while it floated on a cushion of sound, scientists could create ultra-pure glasses and ceramics that were impossible to manufacture on Earth. In the 2000s and 2010s, the technology was democratized. Researchers at the University of Bristol and other institutions began publishing designs for DIY levitators using off-the-shelf Arduino microcontrollers and parking sensor transducers. Suddenly, acoustic levitation wasn't just for NASA, it was for high school science fairs and garage hackers. Simultaneously, the technology evolved from simple trapping to complex manipulation. We moved from one-dimensional levitation, simply holding an object in a line, to three-dimensional manipulation, where arrays of speakers could move an object in any direction, like a real-life tractor beam. No discussion of acoustic levitation is complete without addressing the elephant in the room: the lost technology theories. Alternative history enthusiasts have long speculated that the massive stones of the Great Pyramid of Giza, or the megaliths of Stonehenge, were not moved by ropes and ramps but by sound. Legends from Tibet describe monks using trumpets and drums to lift massive boulders up cliff faces. Arab historians have referenced magic papyrus placed under stones that, when struck with a metal rod, caused the stone to float. Could ancient civilizations have mastered acoustic levitation? The science says it is highly unlikely, at least not in the way we understand physics. First, there is the power problem. As mentioned, levitating a styrofoam ball requires 150 plus decibels of sound. To levitate a 2-ton limestone block, the acoustic energy required would be cataclysmic. It would likely turn the air into plasma or shatter the stone and the eardrums of anyone within a mile before lifting it. Second is the nonlinearity problem. Air is a nonlinear medium at high intensities. If you try to push too much sound energy through it, the wave distorts and loses energy as heat shock waves rather than pressure. There is a physical limit to how much push air can transmit. However, these myths highlight humanity's long-standing intuition that sound is a source of power. While the Egyptians likely didn't use sound to lift blocks, they certainly understood acoustics for resonance in their chambers. The magic of levitation remains, for now, a triumph of modern electricity, not ancient chanting. Levitation is cool, but manipulation is useful. The most exciting developments in the last 5 years have moved beyond simply holding a particle in place. Biologists have long used optical tweezers, which use lasers, to hold individual cells. But lasers produce heat, which can cook or damage delicate biological samples. Enter acoustic tweezers. Because sound waves can travel through human tissue and water without damaging cells, they are the perfect tool for biology. Scientists can now flow blood through a microfluidic chip and use sound waves to push red blood cells into one channel and white blood cells into another, purely based on their density and size. Furthermore, researchers are developing systems that can manipulate objects inside the body. Imagine guiding a drug capsule to a tumor using focused sound waves from outside the skin, then holding it there while it releases its payload. In 2015, a team from the University of Bristol and the Public University of Navarre stunned the world by creating the first working sonic tractor beam. Unlike the standing wave method, which traps an object between a source and a reflector, a tractor beam uses a phased array, a chessboard of tiny speakers that can fire at slightly different times. By carefully timing the waves, they can create a quiet core surrounded by high pressure from only one side. They demonstrated 3 specific shapes of acoustic fields: the tweezer, holding an object like fingers; the vortex, a tornado of sound that traps the object in the eye of the storm; and the bottle, a high-pressure cage that surrounds the object. This technology allows for the UFO abduction scenario where a beam of invisible force reaches out, grabs an object, and pulls it back toward the source. Perhaps the most Black Mirror application of this technology is ultra-haptics, now known as ultraleap. If acoustic radiation pressure can push a polystyrene ball, it can also push your skin. By focusing ultrasonic waves onto a specific point on your hand, these devices can create a sensation of pressure. If you move that focal point around fast enough, faster than your nerves can react, you can trace shapes. Imagine wearing a VR headset and seeing a virtual apple. You reach out, and you feel the curve of the apple. There is nothing there but air, but the sound waves are creating a tactile barrier that your brain interprets as a solid object. In a car, you could have invisible buttons. You reach out to turn up the volume, and you feel a click or a dial in midair, allowing you to control the interface without looking away from the road. Acoustic levitation has graduated from a parlor trick to a serious industrial tool. The biggest challenge in making new drugs is crystallization. When a drug is mixed in a liquid and then dried to form a pill, the way it crystallizes determines how well it works. If it touches the sides of a test tube, the glass acts as a nucleation site, forcing the crystals to grow in a specific, often jagged way. Acoustic levitation allows chemists to dry drugs in midair. With no container to touch, the liquid dries into a perfect sphere. Often, it doesn't crystallize at all. It becomes amorphous. Amorphous drugs dissolve much faster in the human body, meaning higher bioavailability, so you could take a lower dose for the same effect. Research on the drug ibuprofen has shown that acoustically levitated samples can be processed into forms that are significantly more soluble than standard manufacturing methods. In the manufacturing of microchips and watches, components are becoming microscopic. Mechanical tweezers are clumsy, they can scratch delicate surfaces or crush tiny gears. Acoustic levitation offers a soft touch. Assembly lines can now float tiny components into place, rotate them for inspection, and bond them without a human hand or metal tool ever touching them. Tissue engineering is the dream of growing replacement organs. However, cells need a scaffold to grow on. Acoustic levitation allows for scaffold-free tissue growth. By using complex sound fields in what is called an acoustic loom, scientists can levitate thousands of individual cells and force them to aggregate into specific shapes, like a sheet of skin or a tube of a blood vessel. The cells naturally adhere to each other, forming living tissue that hangs in the air during development. We have levitated ants. We have levitated ladybugs. We have levitated gold, water, and plastic. The question on everyone's mind is, when can I fly? The theoretical physics of levitating a human are sound. A human is just a collection of particles, mostly water. If you built a transducer array large enough and powerful enough, you could generate a standing wave with nodes large enough to hold a person. However, there are hurdles. First is the wavelength issue. To levitate a human, approximately 1.7 meters tall, you would need a wavelength larger than the human. This implies a very low-frequency sound, known as infrasound. Low-frequency sound is much harder to focus and requires exponentially more power to generate sufficient pressure. Second is the depth factor. As mentioned, the acoustic intensity required to lift 80 kilograms of mass against gravity is immense. Even if the frequency was inaudible, the pressure fluctuations would likely cause internal hemorrhaging, heat the body tissues rapidly, or stop the lungs from functioning. You might float, but you wouldn't survive the trip. A cheat solution might be used in transportation systems instead. A Hyperloop-style train could, theoretically, glide not on magnets, but on a cushion of high-pressure air generated by acoustic transducers lining the track. This is near-field acoustic levitation, and it is already capable of lifting several kilograms. If you want to build your own, you don't need a PhD. The TinyLev project from the University of Bristol has made this accessible. You need an Arduino Nano, an L298N motor driver, ultrasonic transducers usually harvested from cheap parking sensors, and a 3D printed frame. You arrange the transducers in two opposing domes, wire them up, and the code tells the transducers to fire in a specific phase pattern. You place a small piece of expanded polystyrene foam in the center, power it up, and the foam will snap into the node, floating in midair. Acoustic levitation challenges our perception of reality. It takes the intangible, a sound wave, a vibration of air, and gives it the strength to hold matter. We are currently in the transistor era of this technology. Just as the first transistors were large, clunky, and limited, today's acoustic levitators are restricted to small objects. But the curve of progress is steep. From creating purer medicines that save lives, to enabling new forms of virtual connection where we can touch the digital world, sound is reshaping our future. We are learning to conduct the atmosphere itself, orchestrating a symphony where the instruments are invisible, but the results are solid. The next time you feel the bass thumping in your chest at a concert, remember, that pressure isn't just a feeling, it is a force. And with enough control, that force can move the world.